This problem is a straightforward application of the Nernst equation, but what might be confusing about the problem is that it's actually a combination of a couple of reduction reactions and an oxidation reaction. If you check out all the species in the overall equation, you'll see they actually come from 3 different half reactions. This is possible, and it's actually more true to everyday life that you've got more than one oxidation-reduction reaction happening at the same time. So here we've got neutral lead, and here we've got lead within lead 4 oxide with a +4 charge. Both of them are becoming lead 2 plus ions on the product side. So there's simultaneous reduction of this species and oxidation of this species. So they're both happening at the same time. But as we'll see later on in this problem, we have to evaluate how many moles of electrons are transferred. Well, the difference between 0 and 2 is the same as the difference between +2 and +4. There are 2 moles of electrons transferred in either case. And that'll be important in our calculations later. You can verify this if you go to table 18.1 and you look up all of the half reactions that involve lead. Every single one of them has 2 electrons in it. So N equals 2 when we use the Nernst equation. Okay, so what is the Nernst equation? It allows us to relate non-standard cell conditions to standard cell conditions. So anytime that you're running a cell at concentrations other than 1 molar or pressures other than 1 atmosphere if they're gases, you can use the Nernst equation to correct for those non-standard conditions. They give us a lot of good information right off the bat. They tell us the concentrations of the 2 aqueous species, which is all we need to know in order to find Q. And then they even tell us the standard cell potential. So we'll be plugging those in to do this. Let's look at the equation from the perspective of, let's say you first were studying equilibrium. We're way back in chapter 13 of the book, and I give you this equation. I say, okay, write an expression for either Q or K for this equation. And you'd say, oh, okay, then I'll do products over reactants. I'll raise them to the power of their coefficients. And importantly, I'm going to exclude solids and pure liquids. Well, as it turns out, there's a lot of solids and liquids. On the product side of the equation, it's nothing but solids and liquids. And on the reactant side of the equation, there are 2 solids. Don't write any of those. So it's just 1 over the concentration of hydrogen, and since hydrogen has a coefficient of 2, it's squared, and bicarbonate, and again, bicarbonate has a coefficient of 2, so square that one. And that's it. None of the other chemicals in the equation belong in the reaction quotient. Up above, they gave us the concentrations of hydrogen and bisulfate. So if we plug in, we get 4.5 for each of those, and it's got to be squared. Punch that into your calculator, 1 over 4.5 to the 4th power, if you're multiplying those. And we get a number of 0.00244. Okay, now we know Q. Q is this number. We've got standard cell potential, that's this number. And we've got number of moles of electrons transferred, that's this number. Let's just plug and solve. They gave us 2.04 volts. We had determined that the number of electrons transferred was 2. And when we talk about log here, it's log log, not natural log. And we're going to take the log log of 0.004244. So on my calculator, I'm going to do some punching. And it works out that the whole correction factor is less than 1/10 of a volt. So 2.044 or 2.04 volts minus a negative 0.077 gives us a final answer of 2.12. Notice that that final answer, the non-standard voltage, isn't that far away from the standard voltage of 2.04. It takes a lot of non-standard concentrations and pressures to deflect that voltage very far from the standard voltage.